Good afternoon and welcome to the CVMP 2020 short paper and demo session. I'm Volino from the Centre for Vision, Speech and Signal Processing at the University of Surrey, and I have the honour of serving as this year's short paper and demos chair. Short papers present academic research or innovative industry practice, and demos have always offered the chance for conference attendees to get hands-on with the work. Despite the challenges that have arisen this year, the organising committee has strived to ensure that CVMP maintains its close, interactive and social nature. Through the CVMP Discord server, you will be able to connect directly with short paper and demo authors through their respective channels. The live Q&A session will follow on directly from this, and I encourage you all to participate. Before we start the presentations, I want to quickly thank the generous sponsors who have made it possible for us to deliver this conference completely free of charge. And in particular from the short papers track, a special thanks goes to NVIDIA, who have kindly donated an enterprise-level GPU. This will be awarded to one of the short paper submissions during the closing ceremony tomorrow afternoon. We will now start with the short paper and demo presentations. Thank you.
Good morning, dear audience, and welcome to our presentation of the short paper From a Still Image to a Semantically Aware Video, a Context and Metadata-driven Automatic Media Production Framework. Due to recent technology outbreaks, anyone can become a mass content producer, spreading multimedia content widely and at a high speed in the web. The amount and variety of photos and videos available can be overwhelming, thus bringing new challenges to the marketing industry, specifically in repurposing content for advertisement and publishing promotional content rapidly. To fix this, it is paramount to develop strategies for repurposing, innovating, engaging, and publishing as fast as possible. Yet, doing this by hand would be very hard and very time-consuming. So we have the vision that this can be done in an automatic way if we contextualize the photos as much as possible and the situation where the photo was taken. The collected information can be then stored in the form of metadata and used to automatically select and apply a number of visual effects to create an engaging and meaningful story without forgetting user experience concerns, as the system should be easy to use and any common gadget should be compatible. We have formed a team of content producers together with technologists and market experts in the Photo in Motion Consortium, which is an European-funded project. We have identified real-world needs as well as technical and scientific demands and have decided to use context-aware and artificial intelligence-based approaches. Creating engaging videos for promotional purposes built from a picture has been a common topic in the literature. There are several commercial solutions for producing low-cost videos using predefined animations, but they usually do not consider image content information, thus making them unfeasible for creating object-based animations. Additionally, relevant information for creating automatic summaries can also be obtained by extracting context information using sensors from a mobile phone. This data is not currently being used to infer extra information or fused with content-based information. To understand how the Photo in Motion system interacts, we should analyze the tasks that the user can perform. When taking a photo with the Photo in Motion smartphone app, contextual data is acquired using mobile sensors such as GPS coordinates, motion, and surrounding sounds. This data is later on processed in order to identify the name of the place and events connected to that specific time and place. To annotate the content, we have used transfer learning on neural network models to do region-based tagging and developed algorithms to detect perceptually relevant regions. Afterwards, annotations can be visualized and manually modified in a collaborative tool. The creation of the story involves the use of filters and effects guided by the metadata. Filters are operations that modify static content, and effects are dynamic modifications on the media that change over time. To conclude, this tool automatically produces engaging videos from static media. The solution was built on the requirements of media professionals from several sectors, guaranteeing that it is a value-added product.
Hey, my name is Aaron DeMalder, and this work is part of my engineering doctorate from the Centre for Digital Entertainment in collaboration with VividQ. And thank you for watching this short presentation on artistic control of defocus in computer-generated holography. We all know that lens characteristics form a really crucial part of the feel of an image, and we frequently favour lenses with pleasant features, and spend effort to recreate lens imperfections in render or in post-production in order to add character and charm to shots. Naturally, with our eyes being lenses, we view the world whilst experiencing lens effects such as bokeh, where in out of focus areas we experience points of light defocusing into the image of the limiting aperture, which is our iris. When viewing 3D content in the context of a typical current augmented reality or virtual reality headset, there is no defocus, as the display is merely 2D. But with computer-generated holography, where we modulate the phase of light via a spatial light modulator, we can construct holographic wavefronts that provide a field of light as a simulated real-world view, where the viewer can focus on content within their vision as they would in reality, without vergence accommodation conflict, with raw focusable depth, and with full natural 3D. So bokeh is again an important consideration in forming the final image for the viewer. Here we see that without intervention, the bokeh shape of a holographic image forms the shape of the square eye box. And typically, in order to make this more aesthetically pleasing in an optical system, you would require a physical limiting aperture to achieve the desired defocus shape or f-stop. But, as in computer-generated holography, we're operating in the frequency domain, we can simply mask this aperture in software with very little overhead. And this lets us specify a bokeh shape and lens speed, which is viewable by eye, provided of course that the eye box of the hologram remains smaller than that of the eye of the viewer, or a smaller aperture than that of the lens of a camera that's viewing the hologram. So in order to generate a 3D hologram, we need RGBZ data. And here I've used an EXR render from Redshift in Maya, and we can process it into a suitable intermediate format before feeding it to VividQ's core package, which outputs an image in Fourier space. This is the output hologram that can be displayed on an SLM in order to replay the encoded image data once it's illuminated. Here we see the unmasked hologram and the resulting replay. And if we mask with our desired aperture shape, removing the channel values and the pixels outside of the aperture area, this change is replicated in the replay in the out of focus areas. Typically, this style of mask would be used in image processing to filter frequencies out of the image, such as a low pass, and indeed as a side effect of this we do lose spatial resolution, as shown by the pinhole hologram replay. In order to create the most natural defocus and replicate eye characteristics, we can of course opt to use human-acquired iris aperture shapes. Here we've used some eye scan data from this really cool high-quality eye capture paper and rendered an orthographic map image of the iris geometry. We can then use this mask as our input aperture to match the defocus shape of a given eye at any pupil dilation. This gives us the results that are indistinguishable from real-world eye defocus for this specific viewer, and of course this can be replicated for the second eye, as pupil dilation is linked, but the pupil shape will vary. These masks can get more creative, of course, with varying shapes, animations, or by operating on each color channel individually to add some aberration. These holograms can all be projected as is, and all focus correctly with sharp results at the required depth, and only the defocused areas inherit the effects as intended. In future, using infrared cameras to measure pupil dilation seems a plausible approach to match viewer pupil size, and be able to apply the associated aperture shape. This would also make sure that the aperture of the mask is always the limiting aperture, rather than that of the viewer's pupil, which would ensure that any given artistic bokeh or chosen f-stop can be visible, even as eye box size increases with advances in SLM resolution. This concludes this presentation on artistic control of defocus in computer-generated holography. If you'd like to learn more about computer-generated holography or holographic display, I'd recommend checking out VividQ's website, and I'd also be pleased to answer any questions. Thank you very much.
In this paper, we present a method to estimate the specular anisotropy angle with polarized photometric stereo setup. Our method provides a way to estimate the specular anisotropic characteristics with a reduced cost in hardware setup, when compared with previous methods. In computer graphics, anisotropy is the property of being directionally dependent. An anisotropic surface will change in appearance as it is rotated along its surface normal. In the images shown in this slide, we can see the difference in appearance between isotropic and anisotropic materials. Anisotropy is usually described by the word BRDF, in which the response is characterized as an elliptical lobe, with the longest diameter pointing toward the angle where the maximum response would occur. To successfully model an anisotropic material with the word BRDF, we need to know the angle where the response is maximum, and that leads us to the calculation of the anisotropy angle. In the past, methods that acquire anisotropic properties usually need complex and demanding hardware. Common examples are Gaussian reflectometers and spherical light stages. These setups are high in construction cost and time-consuming in the acquisition process. In contrast, with our proposal, we are able to reduce hardware requirements by using a photometric stereo setup. Good results of specular anisotropy angle can be obtained with a photometric stereo setup containing 6 light sources. This slide shows the specification of our setup. Each light source contains 2 LED lights that is parallel and cross-polarized to the camera lens, respectively, to separate the diffuse and specular response. In this page, we can see the acquired data from individual light sources. With polarizers, we can obtain the pure diffuse response and diffuse plus specular response, respectively. The pure specular response can then be obtained by subtracting the diffuse response from the diffuse and specular response. So the key idea in our method of estimating the specular anisotropy angle is the use of shifted sinusoidal lighting pattern. The pattern was used to separate diffuse and specular response in the past, but we noticed that when we can single out the specular response, integrating the response shows that the specular response would depend only on the phase shift angle, as shown in this slide. We can rewrite the formula for specular response so that it is in the form of a shifted cosine plus a constant term. In this form, we notice that at a certain phase shift angle, the specular response would achieve its maximum. It can be easily shown that the angle corresponds to the specular anisotropy angle. This means that once we collected enough data to recover the formula for the specular response to a shifted sinusoidal pattern, we can use the results to estimate the specular anisotropy angle. As shown in the previous slides, the data we acquired are responses from individual light sources. However, we can simulate the shifted sinusoidal response by post-processing the acquired data with the formula presented in this slide. What we do is that for a given phase shift angle, the data is scaled according to its corresponding sinusoidal value, then summed together. With 6 light sources, we simulate 6 sinusoidal response with different phase shift angles, giving us 6 simulated response to estimate the specular response formula and thus the specular anisotropy angle. In this page, we show the results of an anisotropic fabric. The anisotropy angle is shown on the right. And we also provide the surface normal calculated by the photometric stereo technique. We can see that high-quality anisotropy angle is estimated with our setup and algorithm. In the final page, we show the rendered results using the anisotropic characteristics we estimated. Thank you for listening.
Thank you, Chairperson. My name is Katsushi Suzuki, a researcher at DelightWorks. My team members are Takeshi Okuya and Miss Mihata. Today, I'm going to talk about style transfer in real-time rendering. Let's start with a demonstration. This is a real-time rendering of a style transfer in Unity. From left to right, original rendering, the result of a style transfer reconnect, and optimized. Here is a demonstration of style manipulation in real time. broken down into brightness and color changes. Can you see the zoom up view on the right? The paper texture in the style image is reproduced. We can keep its texture and just change the color of the texture. That's fun, isn't it? Here is the original rendering. Next, style-only transfer. Then, a color-only transfer. Finally, style and color transfer. Neural style transfer in real-time rendering is still slow at Full HD, but as you know, if you make the conversion area smaller, you can reduce the inference time. So we focused on animation technique in which the foreground and background are created separately and move only the foreground character. Our technical contributions are below. First, we created optimized autoencoder model compared with the previous model, LegoNet, and 10.6 times speedups. Second, we shaped up the model size. Finally, we demonstrate a real-time style manipulation with Unity. Real-time style transfer made this possible. I will talk about our method in the next slide. First, we render the entire scene containing the target of the style transfer using normal shaders. Next, we crop the region containing the target character. Then, we apply a style transfer model to this cropped region. Finally, we render the character using the stylized texture. That's all. In this step, we extract the region of the character from a full screen. This makes the computation faster than inputting the full screen into the neural network in the next step. To extract the character regions, we use bone positions. By calculating the 2D screen position of all the bones and get the maximum and minimum values in each direction, we can receive the rectangle containing the character. What is the advantage of using bone positions for region extraction? Firstly, skin meshes are always calculated its bone 3D positions every frames. Therefore, we simply convert them to 2D screen position by matrix multiplication. Secondly, we don't have to scan full screen to extract the region. This is our region extraction method. Let's look at the autoencoder architecture. The left table is the original RegNet model, and the right table is our optimized RegNet model. We reduced the channel size of the convolution 3D layer to speed up the inference by combining two techniques, character area cropping and neural network optimization. Finally, we can style transfer in real time in Full HD 16 fps conditions. This is an inference time comparison of convolution 2D channel numbers. The second line is the number of channels in the convolution layer. As you can see, fewer channels will reduce the inference time. Case 5 is the fastest, but the rough style in the rendered result is gone. Case 3 and Case 4 are good results. I'd like to finish with summary. By extracting character region using bone position, style transfer to a limited area, and an optimized RegNet model, we finally achieved neural network transfer at Full HD 60 fps by using these techniques. The result is a 10.6 times speedups and 82% reduction in model size, and we can now individually manipulate styles and color in real time. For future work, we plan to apply style transfer to multiple characters and deal with arbitrary shapes. Thanks for your attention.
Hello everybody, I am Marco Pesavento, a PhD student at the CVSSP Center at the University of Surrey, and today I'm going to present the work Super Resolution Appearance Transfer for 4D Human Performance Capture. A 4D human performance capture is a 3D reconstruction of a human motion that varies over time. The time itself represents the fourth dimension. State-of-the-art systems for human performance capture typically use small volumes to maximize the camera resolution of the subject. While this maximizes the quality of the reconstruction, it significantly restricts the range of motion of the performer. If we want to performance capture in large volumes, such as the image shown on the left, we cannot simply rely on future increases in camera resolution. In this case of capture, the performer occupies only a small proportion of the field of view of the video cameras, leading to a poor quality in the appearance of the 4D reconstruction compared to a static 3D reconstruction, where the quality of the appearance, as you can see, is much higher due to the smaller capture volume. To tackle this problem, we propose a pipeline that enhances the appearance of a 4D human performance capture by transferring the appearance from a high-resolution static reconstruction without reducing the capture volume. After an initial removal of the background of the input images, the color of the low-resolution capture frames are corrected. First, couple between similar high-resolution images and low-resolution frames are created in the texture map domain. We retrieve partial texture map by applying dense pose, and we create the couples by measuring their similarity with the SSM metric. Then, we extend a state-of-the-art color correction algorithm to use multiple pairs of reference and target image in the learning of a color transfer function, which is applied to all the input frames to correct their colors. Then, the texture map of the model are retrieved and super resolved thanks to a state-of-the-art single-image super-resolution network. In particular, we pre-train the network with a dataset of patches of human texture maps, and we fine-tune it with the original texture map of the input models. From the evaluation, our new algorithm for color correction produces consistent colors in the same frame of different cameras, as you can see in the bottom line. On the other hand, the old algorithm changes the colors of the model for the same frame, producing artifacts in the final reconstruction. As it is shown in the pocket of the right image, the super resolution stage improves the fine details of the model. Here, you can see the comparison between the original 4D performance on the left and the one retrieved after the application of our pipeline on the right. The colors in this last appear to be brighter, and the appearance is therefore enhanced. We are working towards a practical solution to enhance 4D performance capture by leveraging high-resolution static scans to allow capture in larger volumes without sacrificing visual quality. With our approach, we were able to improve the global appearance through color correction and to super resolve the fine details of the model. Thank you for listening. If you have questions, please ask.
We present a smartphone-friendly network for 6DOF object tracking, capable of running on Android and iOS device GPUs, as well as a system for running this and other networks from within Unity 3D, using the TensorFlow Lite C++ API through a native plugin. The network used is based on the architecture from real-time seamless single-shot 6D object pose prediction from Tekken et al., which in turn is a modified version of the YOLO v2 object detection network. The outputs of this network are the corners and centroid of the 3D bounding box of the detected object, from which the pose can be extracted using the perspective and point method. To allow for fast inference on smartphone GPUs, we replaced the Darknet 19 feature extracted with MobileNet v2 and reduced the input size. As this significantly reduces precision, we use simple tracking using separate detection and tracking networks of input sizes 224 by 224 for tracking and 224 by 384 for detection. Tracking starts and resets are handled using the confidence values output by the network. These videos illustrate the improved 3D bounding box outputs when using tracking compared to just
detections on each frame. These videos were generated outside Unity using Python. We now show the live tracking from within Unity 3D on macOS for debugging purposes, iOS, and Android. GPU inference is used in all cases using Metal for macOS and iOS, and OpenCL with OpenGL fallback for Android. For devices that do not support GPU inference, mainly old Android devices, Testable Lite allows for automatic CPU fallback. Devices used here are an iPhone XS and a OnePlus 6. This system allows for any network supported by TensorFlow Lite GPU to be run, as well as several custom sequences of networks, in which the output of the primary network determines the input of the secondary ones. 2 off-the-shelf networks are shown, body pose estimation and hand tracking, as well as a system of multiple models which outputs the segmentation masks of facial features, hair and lips. Thank you for your attention.